everybody. In this video, I want to recap a little bit about confidence intervals and then how to find confidence intervals for means. So we have two kinds of estimates when we're trying to estimate for a population. We have a point estimate, which is a single value estimate. And for a mean, the best point estimate would be the actual sample mean. So if we're trying to estimate what's happening with the population, we could find sample data and then take the average of that and use that as our estimation. What we like better, though, is an interval or like a range of values. Realistically, it is very unlikely that the sample would perfectly match the population. So having an interval tends to be a little bit more realistic of an expectation. So an interval estimate is an interval or a range of values that estimates the population parameter. And that's really what chapter 6 is all about here. So it's about creating confidence intervals, which is a type of interval estimate. And again, we're going to focus on population means, but you could do it for any parameter. So you could do them for proportions or percentages. You could do them for variances and standard deviations, etc. To form an interval estimate, what we do is we start with the point estimate. So we take the sample mean and we basically add and subtract a margin of error. So most of our calculation work has to do with finding that margin of error, and then we're able to add and subtract that. When finding confidence intervals for means and finding the margin of error, we do use two different distributions. So it's going to depend on whether we know the population standard deviation or not. And I apologize, I just caught this mistake. This should be a sigma there, not a mu. Write that in. So it should look like that. We know the population standard deviation, or when we know the population standard deviation, we would use the normal curve or the Z-curve. And if we don't have that information, if we have only sample data, then we use what's called a t-distribution. These curves are very similar looking. They're both bell-shaped, they're both symmetric, and they're both centered at 0. But they do have slightly different widths of the tails and things like that. So they look very similar. You'll see values are very close, but they're not exact. So we do want to be careful and make sure we choose the right one. Another thing to note in general as well is that as our confidence increases, the interval does get wider. So in order to be more confident in our interval, we do have to widen that interval to make sure we really have a better chance of containing the true population value. All right, so let's do some practice. And we're going to start. So I have two examples here. They're both very similar. And what we're going to do is we're just going to start by finding the margin of error in each case. And I'm going to use the tables here for this, but you can also use Excel. Now, in both cases, the confidence level is 98%. The sample size is 30. And then the standard deviation is 5.2. But notice a clear difference here. In this case, you have sigma equals 5.2. So this is population data. Where here you have the, it's written as an S. So this is sample standard deviation. So if you have the population standard deviation, you're using the normal curve or the Z-curve. And when you have the sample standard deviation, you're going to use the t-distribution instead. Now, we do have requirement checks here, so just kind of think back. Remember that in order to actually use any of these formulas, we have to have one of two things happen. Either the population is normal, and we would know that, or our sample size is at least 30. Here, our sample size is 30, so we just make that cutoff, and we can actually proceed with our problem. All right, now I'm going to kind of work them together and show you the difference between the two steps. So in either case, though, you have the same picture pretty much. Again, technically the bell curves look a little bit different, but for hand drawing, I'm not able to draw them well enough to make that difference distinct because they're so close. So you have that 98% in the middle. Right, so you have that 98% right in the middle. And again, for our class, we're doing the more traditional confidence interval, so everything is centered right in that middle there. So this is 98%. So the first thing we should find is the alpha. So what's the leftover piece? So if our confidence interval is 98%, then our alpha here, or if our confidence level is 98%, our alpha would be 2%, right? Because we want those to add to 100. So we're going to have 2% there. We do like to write that in decimal form, so 0.02. And what happens is that half of that goes on each tail. So half of 2% is 1%, or as a decimal 0.01. So what happens is you have 1% here and 1% here. We just split that evenly for, again, a more traditional confidence interval. Now, to use the tables for the normal curve, you have to find the area to the left. So for me, my preferred way to do this is to just find this area right here on the left side. I think it's easier. So we're actually finding the negative of the critical values, but that's fine. So what happens is that 1% is the same thing as 0.01. So we're going to look for that in the table. Don't forget your table in the center has 4 decimal places. So this is actually what we're looking for. All right, let's see. I have a table here. It's a little messy, but not too bad. So I'm looking for 0.01. So looks like it's right in here. So 0.099, 0.0102. The 0.099 is actually a little bit closer. It's 1/10,000th away rather than 2. So I'm going to go ahead and use this one here. So my Z score is going to be negative 2.33. So that negative critical Z is going to be negative 2.33. Now in our formula, we actually use the positive version. So in order to find the error, we take our Z, we multiply it by our standard deviation, and we divide it by the square root of n. And it is the positive version. So we're going to use positive 2.33 here. We're going to multiply by 5.2, and then we're going to go ahead and divide by the square root of 30 in this case. Let me grab my calculator. All right, I just have a calculator app on my phone. So I'm going to go ahead 2.33 times 5.2. I'm going to hit enter there, and then I'm going to divide that by the square root of 30 and hit enter, and I get that my error is about 2.212. And let's see, what did I use here? So it looks like most of my work is 1 decimal place. So I'm going to go ahead and stick with 1 decimal place. So we'll do 2.2 for our error. Now, as a little side note, you can also find the error using Excel. So if you wanted to do this in Excel, the formula there that you're using is confidence.norm. And what you enter is you enter the alpha in decimal form, the standard deviation, and then the n. So our alpha here would be that 0.02. You'd enter the alpha value, your standard deviation of 5.2, and then your sample size. And that is another way to get the error, but using Excel. For the t-distribution, this table is actually very easy to use. So what's happening here is, again, your confidence level is 0.98. Our n is 30. So what we need here instead is the degrees of freedom. And for these calculations, it's going to be n minus 1. So we're going to use 29 there in our table. So I'm going to go to my t-table here. And up top, you have your confidence level. So here we're looking at 98. And my degrees of freedom is 29. So if I go down, I do see I have 29 there. And I'm going to just follow that right over and match that up with the 98. And my value there is 2.462. And then otherwise, it's going to be the same formula. So it's going to be my critical t value times my standard deviation, but I'll use the sample version here. So I have 2.462 multiplied by 5.2 over the square root of 30. Square root of 30. And I get about 2.337. So using 1 decimal place, about 2.3 here. And again, you can see the values are pretty close, right? So the Graphs do look very similar. Again, they're both bell-shaped and symmetric. They're slightly different though, so you do have slightly different answers, but they're going to be pretty close here. So our error is going to be 2.3. You can also do this in Excel. So if you wanted to find the error in Excel, the formula there is confidence dot T instead, and you enter the alpha, the standard deviation, and then the N. So actually same sort of idea as this one over here. Again, don't forget you're getting the alpha, not the tail allowance, but the full 2% there when using Excel. Now on the next page, we're going to take it to the next step and actually create the full confidence interval. And if you flip over to the next page, you'll notice that the information is the same. So it's still 0.98, it's still 5.2, it's still 30 on both cases, but here I'm bringing in the mean. So once you have the error, in order to find the confidence interval, you're just going to add and subtract it with that center. So here our center is 12.3, and our error from the page before was 2.2. And again, we're just going to go ahead and add and subtract. So we're going to get 14.5 and 10.1. So our confidence interval, if we were using the normal curve here, be 10.1 to 14.5. In this case over here, again, same idea. We're going to take that 12.3 and we're going to add and subtract the error. And from the page before, our error there was 2.3. So here we get 14.6 and here we get 10.1. So on this case, 10.0, excuse me. So we have 10.0 is less than the mean, is less than 14.6. Again, very similar answers because the curves are so similar, but different. So you do want to be careful. If you have population data over here, then you can use the Z curve or the normal curve. And if you have sample data, we're using that T table instead. Whether you use Excel or the table, you're still going to do the last step by hand and go ahead and add and subtract. So what's happening here is we're basically 98% confident that the true population mean is going to be in between these values. Now, it's never a guarantee, so you want to keep that in mind, but 98% is a pretty strong confidence. So hopefully we can feel pretty good about this, and ideally, we would go back and maybe do some more research, right? 30 is a pretty small data set still, even though it meets the requirements. So having more data or repeatedly researching topics is always a great idea to be more confident in your population interpretations. All right, the next example, doing a little bit more of a word problem here. From a random sample of 48 business days, from January 4th, 2010 until February 24th, 2017, U.S. gold prices had a mean of 1,368.48. We're going to assume the population standard deviation is 202.60, and we're going to construct the 95% confidence interval here. So read through again carefully. Notice our sample size is 48. Our minimum to use these formulas is 30 if we don't know that the population is normal. So 48 is more than enough. The sample mean was 1368.48, so that's our X bar. And then we're told that the population standard deviation is 202.60. So because we have population data, we're using the normal or that Z curve instead. So our critical value would be our Z value here. Or if you're doing in Excel, you're using the one that has the word or the word norm in it, right? So for normal in this case. So I'm going to do it by hand. And I'm going to just draw, again, a quick picture here. So you have that 95% in the middle. Now, we could go through the whole process of finding the alpha and splitting everything. But because 95 is a common value, you actually have it on your table at the bottom. So your most common confidence levels, again, there's only 4 of them here. It's not all of them. They give you the answer right away. So you can use that Z value of 1.96 here without having to do all the extra work of finding it like we did last time. So our critical Z is 1.96. So we're going to take 1.96. We're going to multiply by that sigma of 202.60, and we're going to divide it all by the square root of 48. If we do that, you get about 57. All right, let's try that again. That made me jump. So it happens when you have mail delivered to your house, apparently. So our value here on the calculator is about $57.32. So you do have to do some rounding there, but you get the error of 57.32. So now once we have the error, we're going to take that, we're going to add it with our mean, and we're going to subtract it with our mean. So we're taking 1368.48, adding it with the 57.32. And when you do this, you get 13, let's see, or 14, excuse me, 25.80. And when we subtract it, we get 1311.16. So what we're seeing here for our confidence interval is we're starting at 1311.16 and we're going up to 1425.80. So we would be 95% confident that this range here actually does contain the true mean for gold prices for the population. Again, when we talk about the final answer, the language is always about confidence. So with 95% confidence, or we are 95% confident. So that is the language that we use there at the end about the population estimation here. So the last piece is it says, from the example above, does it seem possible that the population mean could actually equal the sample mean? So remember our estimate is 1311.16 to 1425.80, and our sample was 1368.48. So first of all, this is definitely in the range, right? So it is possible that the population mean could be exactly 1368.48. However, it's unlikely. It is very rare that we would get a sample that perfectly matches the population. It is possible, right? Lots of things are possible, but unlikely. So it is possible because it, of course, is in that range, but it's unlikely that we would perfectly get the exact answer. It's probably something close to this, but probably not exact. So that's kind of what they're looking for here, is for you to understand that, yes, it is possible that we could always get the exact answer with our sample, but it's very, very unlikely. The chance of that happening would be very small. Because you can see here, we have, quite a range. We have, about $114 in range here of where we think the population mean actually would be. So there's quite a lot of different values that it could be in this case.